Imagine the universe as a vast, darkened theatre where the audience can't see the stage, but occasionally something explodes in the wings with such violence that the flash illuminates every seat in the house. That's essentially our cosmic situation. We're sitting in the dark, applauding the pretty lights, while backstage, stellar catastrophes are rehearsing performances that could end our show permanently. 66 million years ago, the dinosaurs learned this lesson the hard way. As for us, we've built our entire civilization on the assumption that space is mostly empty and harmless, but recent discoveries suggest we might be catastrophically wrong on both counts. The universe, it turns out, is neither empty nor silent. It's simply better at hiding than we are at seeking. Stay with me as we explore what the future holds for humanity. By the end of this journey, you'll understand why astronomers have started sleeping with one eye open, and why the most dangerous thing about our cosmic neighborhood isn't what we can see approaching, but what we can't. Part 1. The dinosaur killer was just the beginning. 66 million years ago, something the size of a mountain fell from space and ended the world as it was known. The asteroid that carved out the Chicxulub crater wasn't just a rock, it was a cosmic reset button, pressed with the force of 10 billion atomic bombs. Picture this, a 10 to 15 kilometer wide chunk of space debris, hurtling through the void at 20 kilometers per second, suddenly encountering our blue marble. In milliseconds, it excavated a crater nearly 200 kilometers across, in what we now call the Yucatan Peninsula. The impact released energy equivalent to 100 million megatons of TNT, roughly 2 million times more powerful than the largest nuclear weapon ever detonated. But the explosion was just the beginning. Within hours, a wall of molten rock and superheated debris rained down across North America. Tsunamis taller than skyscrapers swept across continents. The real killer, though, was what came next, an impact winter that lasted for years. Imagine the sky turning black, not for days or weeks, but for months. Sunlight couldn't penetrate the thick blanket of dust and soot that circled the globe. Without photosynthesis, plants died. Without plants, herbivores starved. Without herbivores, carnivores followed. The food chain collapsed like dominoes, taking 75% of all species with it, including every non-avian dinosaur on the planet. The terrifying truth? Scientists today use Chicxulub as their baseline for cosmic catastrophe, not because it represents the worst that could happen, but because it's simply the most recent example we can study in detail. What keeps planetary defense experts awake at night isn't just the memory of what happened 66 million years ago. It's the knowledge that something bigger could be coming. Here's where things get unsettling. Long-period comets, those icy wanderers from the outer reaches of our solar system, can appear, with virtually no warning. While we've gotten remarkably good at tracking asteroids, comets are different beasts entirely. They originate in the Oort cloud, a spherical shell of frozen debris that extends nearly halfway to the nearest star. When gravitational nudges send one of these ice balls toward the inner solar system, we might have only months or years to spot it, analyze its trajectory, and, if necessary, attempt to deflect it. NASA's DART mission proved that we can nudge small asteroids off course. In 2022, the spacecraft successfully altered the orbit of Dimorphos, a moon orbiting the asteroid Didymos. But comets present unique challenges that make them far more difficult targets. They're traveling faster than asteroids when they reach Earth's neighborhood, sometimes twice as fast. They're also more fragile, composed of loosely bound ice and rock that could fragment under the stress of deflection attempts. And unlike asteroids, which follow predictable paths, comets develop tails and experience non-gravitational forces as they heat up near the sun, making their trajectories harder to predict with precision. Modern sky surveys like ATLAS, Pan-STARRS, and the Zwicky Transient Facility are scanning the heavens nightly, catching more potentially hazardous objects than ever before. These automated sentinels have revolutionized our ability to spot incoming threats, but they're not infallible. Objects approaching from the direction of the sun remain largely invisible until they're uncomfortably close. Southern Hemisphere coverage, while improving, still lags behind northern surveys. The distinction between asteroids and comets matters more than you might think. Asteroids are primarily rock and metal, solid, predictable, and relatively easy to track once discovered. Comets, on the other hand, are cosmic snowballs that become increasingly active as they approach the Sunday. Solar heating causes their icy surfaces to sublimate, creating the spectacular, the tails we admire, but also jets of gas that can alter their trajectories in ways that are difficult to predict. Even more sobering is the scale we're dealing with. The Chicxulub impactor, devastating as it was, measured only 10 to 15 kilometers across, but we now know that much larger comets exist. In the past decade, we've confirmed the existence of comet nuclei measuring over 100 kilometers in diameter, objects that would make the dinosaur killer look like a pebble by comparison. And then there are the truly unknown quantities, the interstellar visitors. In 2017, we got our first confirmed look at an object not born in our solar system when Oumuamua streaked through the inner solar system. 2 years later, Comet Borisov followed suit. These interstellar wanderers reminded us that space is not empty, and that visitors from other star systems pass through our cosmic neighborhood more frequently than we previously imagined. As we peer deeper into space with increasingly sophisticated instruments, we're beginning to comprehend the true inventory of objects that could, theoretically, find their way to Earth. The sobering reality is that if the Chicxulub impact was just a warm-up act, the main event could be something far more catastrophic than anything our species has ever witnessed. What happens when the cosmos decides to throw something truly massive our way? Part 2. The Great Comets of History. Some comets don't just visit our skies, they dominate them. These are the great comets, the ones that burn themselves into human memory and remind us that we share our solar system with some truly spectacular and potentially terrifying wanderers. Take Hale-Bopp, the superstar of 1997. For 18 months, an almost unprecedented length of time, this cosmic visitor was visible to the naked eye, casting an eerie glow across Earth's night sky. What made Hale-Bopp so special wasn't just its brightness, but its sheer size. With a nucleus estimated at 60 kilometers across, it was a genuine giant among comets. As it approached the Sun, its coma, the glowing envelope of gas and dust surrounding the nucleus, expanded to nearly 4 million kilometers in diameter, larger than the Sun itself. But Hale-Bopp wasn't just a scientific marvel, it was a cultural phenomenon. Millions of people stepped outside to witness what many described as the most spectacular comet of their lifetimes. Yet beneath the wonder lay an undercurrent of unease. Here was visible proof that enormous objects from the outer solar system could appear in our cosmic neighborhood with relatively little warning. Hale-Bopp had been discovered only 2 years before its closest approach to the Sun, a cosmic blink of an eye. History is filled with such unexpected visitors. The Great Comet of 1811, sometimes called Napoleon's Comet, blazed across European skies for months. With a coma larger than the Sun and a tail stretching 60 degrees across the sky, it was impossible to ignore. Superstitious observers linked its appearance to the military campaigns that would lead to Napoleon's downfall in Russia. While we now know better than to attribute earthly events to celestial visitors, the comet's timing seemed almost ominous to those who witnessed it. These great comets share certain characteristics that both fascinate and unsettle astronomers. They often experience dramatic brightening events called outbursts, where the nucleus suddenly becomes more active, ejecting massive amounts of material and causing the comet to flare in brightness by factors of hundreds or even thousands. These outbursts are unpredictable and poorly understood, reminding us how little we truly know about the behavior of these icy time capsules from the early solar system. The eerie green glow that many comets display, including some recent visitors, has sparked countless conspiracy theories and alien speculation. The reality is both more mundane and more beautiful. That ghostly green light comes from diatomic carbon molecules and cyanogen fluorescence, simple chemistry occurring as solar radiation energizes the comet's coma. It's not alien technology or toxic gas. It's the same carbon that forms the backbone of all life on Earth, glowing in the vacuum of space. Yet the sudden appearance of these great comets continues to humble astronomers. Before our current generation of automated sky surveys, most comets were discovered by amateur observers or stumbled upon by accident. Even today, with our sophisticated detection networks, We occasionally get surprised by comets that seem to appear from nowhere, already bright enough to see with the naked eye. The geometry of comet encounters plays a crucial role in both their spectacular appearance and their potential threat level. A comet's perihelion, its closest approach to the Sun, determines how much solar heating it experiences. More heating means more outgassing, which creates larger, more spectacular tails but also makes the comet's trajectory less predictable. Some comets, like Atlas C divided by 2019 L3, literally fall apart under this thermal stress, fragmenting into multiple pieces as they round the Sunday. What makes these historical great comets particularly unsettling from a planetary defense perspective is their reminder that large, active objects regularly enter the inner solar system. While their spectacular tails and bright appearance make them seem threatening, it's important to remember that visibility doesn't equal danger. A comet's brightness depends on its size, composition, distance from both the Sun and Earth, and viewing geometry. A relatively small comet passing close to Earth might appear brilliant, while a much larger one passing at a greater distance might barely be visible. Throughout history, comets have served as harbingers of doom in human cultures worldwide. Ancient Chinese astronomers meticulously recorded comet appearances, often interpreting them as omens of dynastic change. Medieval Europeans saw them as signs of divine displeasure, harbingers of plague, war, or famine. While we've outgrown such superstitions, there's something primal about the fear these visitors inspire, perhaps an evolutionary memory of genuine cosmic threats our ancestors witnessed. The anthropological connection between comets and catastrophe isn't entirely misguided. While most comets pose no threat to Earth, they serve as visible reminders that space is not empty, that objects from the outer reaches of our solar system can and do venture into our cosmic neighbourhood. Each great comet we witness is essentially a preview of the kinds of objects that populate the distant Oort cloud, a vast reservoir of potential visitors that we're only beginning to understand. As we'll see, some of these visitors aren't even natives of our solar system. And if surprise is what makes great comets so unsettling, what should we make of visitors that aren't even bound to our Sun? Part 3. The Alien Visitor, 3I-ATLAS. 2025 has given us something unprecedented, confirmation of the third known interstellar object to visit our solar system. Designated 3I-ATLAS, or more formally C divided by 2025 N1, this cosmic wanderer has earned the distinction of being only the third confirmed visitor from beyond our solar system, following the mysterious Oumuamua in 2017 and Comet Borisov in 2019. What makes an object interstellar isn't just where it came from, but where it's going. Unlike comets and asteroids born in our solar system, which follow elliptical orbits bound to the Sun, interstellar objects travel on hyperbolic trajectories. In simple terms, they're moving so fast that our Sun's gravity can bend their path but can't capture them. They swing through our solar system once, and then continue into the void, never to return. The media has latched onto 3I-ATLAS's glowing, green appearance, with some outlets breathlessly speculating about alien technology. The reality is far more prosaic but no less fascinating. That eerie green glow is almost certainly the same phenomenon we see in ordinary comets, fluorescence from diatomic carbon and cyanogen molecules energized by solar radiation. It's not evidence of extraterrestrial engineering. It's evidence that interstellar space contains the same basic building blocks of chemistry that we find throughout our own solar system. 3I-ATLAS reached perihelion, its closest approach to the Sun, on October 29, 2025, at a distance of roughly 2.5 astronomical units, placing it beyond the orbit of Mars. This timing provided astronomers with a precious opportunity to study an interstellar visitor during its period of maximum activity, when solar heating would cause it to outgas most vigorously and reveal clues about its composition. For scientists, 3I-ATLAS represents a unique laboratory, a chance to compare the composition and behavior of an object formed around another star with comets native to our own solar system. The questions they're asking are profound. Do interstellar comets contain the same mix of ices and organic compounds as our local comets? How do stellar nurseries in different parts of the galaxy differ in their chemistry? What can this visitor tell us about the conditions that existed when and where it formed, possibly billions of years ago? The discovery of 3I-ATLAS follows a now familiar pattern. Automated survey systems like ATLAS, the Asteroid Terrestrial Impact Last Alert System, first spotted what appeared to be a routine comet or asteroid. But follow-up observations revealed something extraordinary. The object's trajectory was hyperbolic, indicating it was moving too fast to be gravitationally bound to our solar system. Confirmation required multiple observations over several weeks, tracking the object's precise path through space to eliminate any possibility of measurement error. Here's what should keep you awake at night. If we've detected 3 interstellar objects in less than a decade, how many fainter ones have passed through unnoticed? Our current detection capabilities are biased toward objects that are either large, highly reflective, or actively outgassing. A dark, inactive interstellar asteroid, particularly one approaching from the direction of the Sun, could easily slip past our surveys entirely. The speed of interstellar objects presents unique challenges for planetary defense. 3I-ATLAS, like its predecessors, is traveling at roughly 30 kilometers per second relative to the Sun, significantly faster than typical solar system objects. At these velocities, even if we detected a dangerous interstellar object years in advance, deflecting it would require fundamentally different techniques than those being developed for conventional asteroids and comets. But let's address the elephant in the room, the persistent speculation about extraterrestrial technology. NASA, ESA, and other space agencies maintain that all 3 confirmed interstellar objects are consistent with natural phenomena. However, they're also taking these claims seriously enough to study each visitor with unprecedented intensity. The scientific method demands that we examine all possibilities, even exotic ones, while maintaining appropriate skepticism. The Oumuamua controversy illustrates this balance perfectly. When the object exhibited slight non-gravitational acceleration, speeding up in ways that couldn't be explained by gravity alone, some researchers proposed exotic explanations ranging from light sails to alien probes. The mainstream scientific community, however, has converged on more conventional explanations. Outgassing of hydrogen or sublimating organic compounds, creating tiny thrusts, or even the radiation pressure from the Sun acting on an unusually shaped object. Comet Borisov, by contrast, behaved exactly like typical comet, complete with a normal coma and tail. Its composition, as revealed by spectroscopic analysis, closely matched that of comets from our own Oort cloud, suggesting that the basic processes of planetary formation and comet composition may be universal features of stellar systems. What makes 3I-ATLAS particularly intriguing is that it appears to be exhibiting typical cometary activity while clearly being an interstellar visitor. This gives astronomers the best of both worlds, a chance to study an alien object, displaying familiar behavior, allowing for direct comparison with our solar system's native population. The implications extend beyond pure science. These interstellar visitors are testing our detection and response capabilities, the same systems we're developing to protect Earth from conventional threats. Every hyperbolic trajectory we track, every composition measurement we make, every behavioral quirk we catalogue is improving our ability to distinguish between natural phenomena and potentially artificial objects. The uncomfortable truth is that if interstellar visitors are common enough for us to detect 3 in less than a decade, they're probably far more common than we previously imagined. Most are likely too small, dark, or inactive to detect with current technology, but as our survey capabilities improve, we should expect to find more of these cosmic travelers passing through our celestial neighborhood. And if alien snowballs are indeed a regular occurrence, what about alien ice mountains? What might be lurking in interstellar space that we haven't yet learned to see? Part 4. The Monster Approaching. Bernardinelli Bernstein. In the catalogue of cosmic nightmares, few objects inspire quite the same mixture of fascination and dread as C, divided by 2014 UN 271, better known as Comet Bernardinelli Bernstein. Discovered in 2021 through painstaking analysis of dark energy survey data, this object holds the distinction of being the largest comet nucleus ever measured, a cosmic monster stretching approximately 137 kilometers across. To put that size in perspective, Imagine a mountain range floating through space. Most comet nuclei measure just a few kilometers in diameter, dirty snowballs that could fit comfortably within a major city. Bernardinelli-Bernstein is different. At 137 kilometers across, it's larger than Rhode Island. Its volume is roughly 1 million times greater than a typical comet, containing enough ice and rock to fill a significant fraction of Earth's oceans if melted. The discovery story itself reads like a detective novel. Astronomers Pedro Bernardinelli and Gary Bernstein were mining through years of archived data from the Dark Energy Survey, a project primarily focused on mapping the universe's large-scale structure. Hidden in those images, recorded between 2013 and 2019, was something unexpected: a slowly moving object in the outer solar system. Additional observations confirmed what the data suggested. This was no ordinary trans-Neptunian object, but a comet of unprecedented size. When Bernardinelli-Bernstein reaches perihelion in 2031, it will approach within 10.9 astronomical units of the Sun, still well beyond Saturn's orbit and posing absolutely no threat to Earth. But that distance masks the truly terrifying aspect of this object. It's a preview of what might be lurking in the outer reaches of our solar system. The Hubble Space Telescope and other instruments have confirmed the comet's enormous size through careful thermal modelling. As Bernardinelli-Bernstein slowly approaches the Sun, solar heating causes its surface ices to sublimate, creating a measurable coma. By analysing the brightness and thermal emission of both the nucleus and its surrounding envelope, astronomers calculated that the solid nucleus itself spans roughly 137 kilometres, making it not just the largest comet ever observed, but possibly the largest object in the Oort cloud. Here's where the mathematics become sobering. If an object like Bernardinelli-Bernstein were to impact Earth, and let's be absolutely clear that this particular comet poses no such threat, the consequences would be literally unimaginable. The kinetic energy of a 137-kilometer object, travelling at typical comet speeds, would be roughly 1,000 times greater than the Chicxulub impact that ended the age of dinosaurs. Such an impact would represent a civilization-ending event of the highest order. The explosion would excavate a crater several hundred kilometers across, instantly vaporizing everything within thousands of kilometers of the impact site. The atmospheric shock would trigger global earthquakes and volcanic eruptions. Ocean impacts would generate tsunamis that would scour continents clean. The long-term climate effects would make the post-Chicxulub impact winter look mild by comparison. But let's step back from the nightmare scenario and focus on what Bernardinelli-Bernstein actually teaches us. Its existence proves that genuine giants inhabit the Oort cloud, the vast spherical shell of icy debris that surrounds our solar system. This distant reservoir, extending roughly halfway to the nearest star, contains the remnants of our solar system's formation 4.6 billion years ago. Most of its contents remain frozen and invisible, but occasionally, gravitational perturbations send objects tumbling toward the inner solar system. The discovery of Bernardinelli-Bernstein suggests that our understanding of the Oort cloud's population has been incomplete. If objects this large exist, and remember, this one was only discovered because it happened to pass through the relatively narrow field of view of one particular survey, how many others remain undetected in the outer darkness? From a planetary defense perspective, objects like Bernardinelli-Bernstein present unique challenges. Their immense size would make them virtually impossible to deflect using current or planned technologies. Kinetic impactors like the DART mission would be ineffective against such massive targets. Nuclear explosives might fragment them, but the resulting debris field could pose an even more widespread threat. The most realistic defense would be early detection and evacuation, assuming we had decades or centuries of warning. Fortunately, the orbital mechanics of long-period comets work in our favor for detection. Objects like Bernardinelli-Bernstein take millions of years to complete their journeys from the outer Oort cloud to the inner solar system. Unlike potentially hazardous asteroids, which might be discovered only months or years before a close approach, true long-period comets can be detected decades before they reach dangerous proximity to Earth. The upcoming Vera Rubin Observatory promises to revolutionize our ability to detect such objects. When it begins operations, This facility will survey the entire visible sky every 3 nights, detecting moving objects far more efficiently than current surveys. Computer models suggest it could increase our discovery rate of long-period comets by orders of magnitude, finally giving us a comprehensive inventory of what's lurking in the outer solar system. The media coverage of Bernardinelli Bernstein illustrates both the opportunities and dangers of science communication in the digital age. Headlines often emphasize the object's enormous size while downplaying the fact that it poses no threat to Earth. This creates a challenging balance for scientists. How do you convey the genuine scientific significance of such discoveries while avoiding unnecessary public alarm? The answer lies in context and education. Bernardinelli Bernstein is remarkable precisely because it's so rare. Its enormous size makes it a unique laboratory for studying the composition and structure of pristine solar system materials. Its predictable trajectory gives astronomers years to plan detailed observations. Its distance ensures that we can study it safely, without any risk to Earth. Yet the deeper implication remains unsettling. If a 137-kilometer comet can exist, what's the upper limit? How big do these cosmic monsters get? Part 5. Hypothetical doomsday comets. Let's venture into the realm of pure speculation, the kind of scenario that keeps planetary defense specialists staring at the ceiling at 3 a.m. Imagine, if you will, 2 hypothetical comets, Thanatos, measuring 300 kilometers across, and Leviathan, a 500-kilometer monster that dwarfs even Bernardinelli Bernstein. These are thought experiments, not real objects, but they represent the kinds of cosmic nightmares that could theoretically exist in the outer reaches of our solar system. Thanatos, our hypothetical 300-kilometer comet, would contain roughly 27 times more mass than Bernardinelli Bernstein. If such an object were to impact Earth, and remember, we're firmly in the realm of speculation here, the consequences would transcend anything in Earth's recorded geological history. The impact would release energy equivalent to roughly 100 million megatons of TNT, creating a crater over 1,000 kilometers across and triggering earthquakes that would register magnitude 10 or higher on the Richter scale. Seismic events so powerful they would literally crack the planet's crust. But Leviathan, our 500-kilometer hypothetical monster, would make even Thanatos look modest. An impact from such an object would release energy comparable to the formation of Earth's moon, the kind of collision that planetary scientists believe occurs perhaps once in a solar system's entire history. We're talking about forces that could literally blow away Earth's atmosphere and boil the oceans into space. Here's a crucial point that often gets lost in sensationalist discussions. Size alone doesn't determine orbital mechanics. Even a 500-kilometer comet wouldn't gravitationally destabilize Earth's orbit unless it passed absurdly close, within a few Earth radii. The real danger from such objects isn't gravitational disruption, it's the catastrophic release of kinetic energy upon impact. The physics of comet deflection becomes meaningless at these scales. Current planetary defense strategies rely on delivering relatively small amounts of energy to slightly alter an object's trajectory over time, the principle demonstrated by NASA's successful DART mission. But kinetic impactors would be utterly useless against objects this massive. Even nuclear explosives, often proposed as last resort deflection tools, would be like trying to stop a freight train with a firecracker. This is where the volatile nature of comets becomes both a blessing and a curse. Unlike solid metallic asteroids, comets are loosely bound collections of ice, rock, and organic compounds. The same thermal stress and outgassing that makes them spectacular could also make them prone to fragmentation. In theory, a precisely targeted nuclear explosion might break up a large comet, but the resulting debris field could pose an even more widespread threat than the original intact object. The detection timeline for such massive objects would be both our salvation and our torment. Objects this large would be visible to our current surveys decades before reaching the inner solar system, assuming they approach from a favorable direction. But confirmation of their trajectories and threat assessment would take months or years, during which time public panic could become as destructive as the cosmic threat itself. Here's where our current blind spots become particularly concerning. Most of our asteroid and comet detection systems are located in the northern hemisphere, creating gaps in southern hemisphere coverage. Objects approaching from the direction of the sun remain largely invisible until they're uncomfortably close. And comets arriving from high-inclination orbits, above or below the plane of the solar system, might evade detection until relatively late in their approach. The upcoming Vera Rubin Observatory will dramatically improve our detection capabilities, scanning the entire visible sky every few nights and cataloguing moving objects with unprecedented efficiency. Computer simulations suggest it will detect hundreds of thousands of new asteroids and comets, finally giving us a comprehensive census of potentially hazardous objects in our cosmic neighbourhood. But even the most sophisticated surveys can't eliminate every blind spot. Comets can experience dramatic changes in brightness due to outgassing and fragmentation events. An object that appears small and harmless might suddenly flare to many times its original brightness, revealing a much larger nucleus than initially estimated. Conversely, a large comet might appear deceptively faint if its surface becomes covered with non-volatile materials that suppress outgassing. The timescales involved in hypothetical megacomet encounters would be both blessing and curse. While we might have decades of warning, the public's psychological impact could be devastating. Imagine learning that a civilization-ending object was approaching Earth with mathematical certainty. How would governments respond? How would markets react? Would international cooperation prevail, or would nations turn inward in preparation for catastrophe? The uncomfortable truth is that our planetary defense capabilities, while improving rapidly, remain woefully inadequate for truly massive threats. We're developing techniques that might work against city-killer asteroids, objects tens to hundreds of meters across. We've demonstrated our ability to deflect small asteroids like Dimorphos, but against hypothetical giants like Thanatos or Leviathan, our best defense would be early detection, followed by what? Mass evacuation? Underground shelters? Long-term survival preparations? These scenarios force us to confront the limits of human technological capability. We are, quite literally, one cosmic accident away from extinction. The only comfort, and it's cold comfort indeed, lies in the mathematical improbability of such events occurring within human timescales. The larger the potential impactor, the rarer it becomes. Yet the universe has already demonstrated its capacity for shocking surprises. Who predicted the existence of interstellar visitors like Oumuamua? Who anticipated finding a 137-kilometre comet like Bernardinelli Bernstein? As our surveys become more sensitive and comprehensive, we're discovering that the solar system contains more large objects than previous models predicted. If ice mountains like these represent the extreme end of solar system threats, what other predators might be lurking in the cosmic dark? Objects that make even 500-kilometre comets look like harmless dust motes. Part 6. The Invisible Killers, Rogue Black Holes. Somewhere in the darkness between stars, invisible predators drift through our galaxy like cosmic sharks, stellar mass black holes that have been ejected from their birth systems and now wander freely through interstellar space. Until recently, these rogue black holes existed primarily in computer simulations and theoretical papers. But in 2022, the Hubble Space Telescope gave us our first confirmed glimpse of one of these invisible killers. The discovery came through gravitational microlensing, a phenomenon Einstein predicted but never expected we'd be able to observe directly. When a massive object passes between Earth and a distant star, its gravity acts like a lens, temporarily magnifying the star's light. For 6 years, Hubble tracked one such event, watching as an invisible object's gravity distorted the light from a star, 25,000 light-years away. The meticulous analysis that followed revealed something extraordinary. A black hole roughly 7 times the mass of our Sun, drifting alone through the galaxy at about 45 kilometers per second. This wasn't just an academic curiosity, it was proof that our worst cosmic fears might be justified. Astronomers estimate there are approximately 100 million stellar mass black holes scattered throughout the Milky Way, most of them completely invisible, detectable only when they happen to pass between us and more distant light sources. The vast majority remain hidden in the darkness, following trajectories we can't predict, carrying enough gravitational influence to disrupt planetary systems if they pass too close. But what does too close actually mean when we're talking about rogue black holes? The mathematics are both reassuring and terrifying. A stellar mass black hole would need to pass within roughly 1,000 astronomical units of our solar system, about 25 times the distance to Pluto, to significantly perturb Earth's orbit. At that distance, its tidal forces would begin stretching and compressing our planet's crust, triggering massive earthquakes and volcanic eruptions long before it actually captured Earth or flung us into interstellar space. The odds of such an encounter are mercifully small, roughly comparable to winning the lottery several times in a row, but the consequences would be absolute. Unlike asteroid impacts, which might destroy civilization but leave the planet intact, a close encounter with a rogue black hole would fundamentally alter Earth's position in the solar system, making our world uninhabitable for billions of years. The discovery of that first confirmed rogue black hole has revolutionized our understanding of galactic demographics. Computer models suggest these objects are created during the violent supernova explosions that mark the deaths of massive stars. If the explosion is asymmetric, if more material gets ejected in one direction than another, the newborn black hole receives a natal kick that can accelerate it to hundreds of kilometers per second, fast enough to escape its parent star system entirely. Some of these cosmic refugees have been wandering the galaxy for billions of years, invisible hitchhikers carried along by the Milky Way's rotation, but not gravitationally bound to any particular star system. They're fossils of ancient stellar catastrophes, black holes that witnessed the galaxy's youth and have been drifting through space since before our solar system even formed. The detection challenge is immense. Black holes don't emit light, they absorb it. The only way to find isolated black holes is through their gravitational effects. Microlensing events like the one Hubble observed, or the gravitational waves they produce when they collide with other massive objects. The upcoming Nancy Grace Roman Space Telescope will dramatically improve our microlensing capabilities, potentially revealing thousands of additional rogue black holes currently hidden in our galactic neighborhood. But here's where the story takes an unsettling turn. The black hole Hubble discovered wasn't the largest or most dangerous of its kind. It was simply the first one we happened to catch in the act of lensing a background star. Recent discoveries suggest the population of massive stellar remnants wandering our galaxy might be far larger and more diverse than we previously imagined. Consider BH3, discovered in 2024 through analysis of data from the European Space Agency's Gaia mission. This stellar mass black hole, located just 2,000 light-years from Earth, weighs in at roughly 33 solar masses, making it the most massive stellar black hole found in our galaxy. Unlike the isolated rogue black hole detected by Hubble, BH3 has a companion star, which is what made its discovery possible. But its enormous mass raises uncomfortable questions about how many similar giants might be drifting unseen through interstellar space. The physics of black hole encounters becomes increasingly surreal as we consider closer approaches. At distances of a few dozen astronomical units, roughly the scale of our outer solar system, a rogue black hole wouldn't just perturb planetary orbits. It would begin shredding the outer planets themselves through tidal forces. Jupiter's moons would be scattered like pool balls. Saturn's rings would be twisted into spirals before being consumed entirely. Even more disturbing is the realization that we might not see such an intruder coming. Unlike comets, which brighten as they approach the sun, black holes remain invisible until they're close enough for their gravitational effects to become apparent. By the time we detected the orbital perturbations of outer planets, the rogue black hole might be close enough that evacuation would be impossible and deflection unthinkable. The Roman Space Telescope, scheduled for launch in the mid-2020s, represents our best hope for cataloguing these invisible threats. Its wide-field infrared camera will monitor hundreds of millions of stars simultaneously, watching for the telltale signs of microlensing events that reveal hidden massive objects. Computer simulations suggest it might detect dozens of rogue black holes per year, finally giving us a statistical understanding of how many of these objects populate our galactic neighborhood. Yet even improved detection capabilities can't eliminate the fundamental uncertainty. We're essentially playing a cosmic game of hide and seek with invisible objects that could end human civilization without warning. The universe contains billions of stellar mass black holes, most of them completely dark, following trajectories shaped by gravitational interactions that occurred long before Earth existed. What keeps astronomers awake isn't the certainty of catastrophe. The odds remain vanishingly small. It's the knowledge that somewhere in the darkness between stars, invisible predators are drifting through space, carrying enough gravitational influence to reshape solar systems. We've finally proven they exist, but we've barely begun to understand how many are out there, where they're going, or when one might wander close enough to remind us how fragile our cosmic situation really is. And if lone stellar mass black holes represent the small fry of cosmic predation, what about the supermassive beast that lurks at the very heart of our own galaxy? Part 7. The Supermassive Hunger. At the centre of our galaxy lies a monster so massive it defies comprehension, Sagittarius A star, a supermassive black hole weighing roughly 4 million times as much as our Sunday. For most of human history, this cosmic leviathan remained hidden behind clouds of dust and gas, invisible to optical telescopes, but betraying its presence through the frenzied dance of nearby stars. In 2022, the Event Horizon Telescope finally gave us our first direct image of this galactic predator, revealing the glowing ring of superheated matter spiraling toward oblivion at its event horizon. To put Sagittarius A star's mass in perspective, imagine trying to compress 4 million suns into a region smaller than Mercury's orbit. The gravitational field is so intense that matter orbiting near the event horizon reaches speeds approaching 20% of light speed before vanishing forever. Stars that venture too close are torn apart by tidal forces in spectacular events called tidal disruption flares, their stellar material forming brilliant accretion disks before disappearing into the void. But here's what should provide some comfort. Sagittarius A star currently poses no direct threat to Earth. At roughly 26,000 light-years from our solar system, we're safely nestled in the galactic suburbs, far from the chaos that surrounds our galaxy's central engine. The black hole isn't going to suddenly wake up and vacuum Earth into its maw like some cosmic drain cleaner. Black holes don't work that way. They're not cosmic vacuum cleaners indiscriminately sucking up nearby matter. However, Sagittarius A star hasn't always been the relatively quiet giant we observe today. Evidence suggests it experienced periods of intense activity in the recent cosmic past, episodes that painted our galaxy in high-energy radiation and left traces we can still detect today. The most striking evidence comes from the Fermi Gamma Ray Space Telescope, which revealed enormous bubbles of energized gas extending 50,000 light-years above and below the galactic plane. These Fermi bubbles are the cosmic equivalent of exhaust plumes, remnants of titanic outbursts that occurred roughly 2 to 4 million years ago. What could cause such violent episodes? The answer lies in the feeding habits of supermassive black holes. Currently, Sagittarius A star exists in a relatively starved state. There simply isn't much nearby matter for it to consume. But occasionally, gas clouds, disrupted stars, or even smaller black holes fall into its gravitational well, providing fuel for spectacular outbursts. When a supermassive black hole feeds actively, it doesn't just grow larger, it becomes a quasar, one of the most luminous objects in the universe. Imagine if Sagittarius A star suddenly transitioned from its current dormant state to full quasar mode. The radiation output would increase by factors of thousands or millions. While Earth's distance provides significant protection, such an outburst would still bathe our solar system in unprecedented levels of high-energy radiation. The immediate effects would be largely invisible. Cosmic rays and gamma radiation don't produce spectacular light shows in Earth's atmosphere. But over time, the increased radiation could affect our planet's climate and atmospheric chemistry in subtle but potentially significant ways. The mechanics of such outbursts involve physics that pushes the boundaries of human understanding. As matter spirals toward the black hole, it forms an accretion disk that heats to billions of degrees. Magnetic field lines threading through this disk can launch jets of material at near-light speed, creating focused beams of energy that stretch across thousands of light-years. If Earth happened to lie along one of these jet directions during an active phase, the consequences could be far more severe than the diffuse radiation from a typical quasar outburst. Recent observations using the Event Horizon Telescope have revealed that Sagittarius A star is already showing signs of structure in its immediate environment. Polarized light observations suggest complex magnetic field configurations around the black hole, the same kinds of fields that could, under the right conditions, launch powerful jets. While the black hole remains relatively quiet today, these magnetic structures indicate it retains the potential for much more dramatic activity. The timescales involved in supermassive black hole variability span from minutes to millions of years. Sagittarius A star exhibits small-scale flaring on timescales of hours, as small amounts of matter cross the event horizon. But the major outbursts that created the Fermi bubbles occur over much longer periods, sustained feeding episodes that might last hundreds of thousands of years. What triggers these major episodes remains an active area of research. Computer simulations suggest several possibilities: the disruption of massive star clusters near the galactic center, the capture of intermediate mass black holes, or the collision of gas-rich smaller galaxies with our own. Any of these events could dump enormous amounts of material into Sagittarius A star's gravitational well, potentially triggering another quasar-like outburst. The psychological impact of living with a 4 million solar mass black hole at the center of our galaxy is fascinating to consider. For most of human history, we were completely unaware of its existence. Now that we know it's there, now that we've actually photographed its shadow, how should that knowledge affect our cosmic perspective? We're essentially living in a galaxy with a loaded gun at its center, one that could theoretically fire at any moment. Yet this knowledge also provides a strange form of comfort. Sagittarius A star has existed in roughly its current state for billions of years. Our solar system has orbited the galaxy dozens of times during this period, experiencing whatever radiation environment the central black hole creates. Life on Earth has evolved under these conditions. In a very real sense, we're adapted to living in a galaxy with an active galactic nucleus. The real uncertainty lies not in whether Sagittarius A star might become active again. It almost certainly will, given enough time, but in when such activity might occur and what form it might take. The black hole operates on cosmic timescales that dwarf human civilization. An outburst that seems sudden from a galactic perspective might unfold over thousands of human generations. Modern astronomy has given us the tools to monitor our galactic center with unprecedented precision. Radio telescopes track the orbits of stars close to Sagittarius A star, watching for signs of disruption that might herald increased activity. X-ray and gamma-ray satellites monitor the black hole's current output, looking for changes that might indicate the beginning of a more active phase. But perhaps the most unsettling aspect of Sagittarius A star isn't its potential for future outbursts. It's the reminder that our entire galaxy is, in a very real sense, organized around this supermassive predator. Every star in the Milky Way, including our Sun, follows an orbit ultimately determined by the gravitational influence of this central monster. We're not just living near a supermassive black hole, we're living in a gravitational system that exists because of it. If the sleeping giant at our galaxy's heart represents a distant threat, what about the cosmic phenomena that could reach across intergalactic space to remind us that the universe contains even larger predators? Part 8. Other Cosmic Giants. Beyond black holes lurk other cosmic giants capable of unleashing destruction across galactic distances, stellar phenomena so energetic they can be detected from billions of light-years away. These are the universe's heavy artillery: neutron star collisions, magnetars, and gamma-ray bursts that release more energy in seconds than our Sun will produce over its entire 10 billion-year lifetime. On August 17, 2017, humanity witnessed something unprecedented: the collision of two neutron stars, detected simultaneously by gravitational wave observatories and optical telescopes. The event, designated GW170817, marked the dawn of multi-messenger astronomy, our first glimpse of a cosmic catastrophe through both the ripples it created in space-time and the light it produced. Neutron stars represent matter compressed to unimaginable densities, objects where a teaspoon of material would weigh as much as Mount Everest. When two such objects spiral into each other over millions of years, the final merger releases gravitational waves that stretch and compress space itself as they race outward at light speed. But the electromagnetic fireworks are equally spectacular. The collision creates a kilonova, an explosion that outshines entire galaxies for weeks and forges heavy elements like gold, platinum, and uranium in quantities that dwarf the production of ordinary stellar nucleosynthesis. The gold in your jewelry, the platinum in your car's catalytic converter, these elements were likely forged in neutron star collisions billions of years ago, scattered into space by explosions visible across the observable universe. We are, quite literally, made of stellar catastrophes. But some neutron stars don't wait for collisions to unleash their fury. Magnetars, neutron stars with magnetic fields trillions of times stronger than Earth's, occasionally experience starquakes that crack their crusts and release more energy in milliseconds than our Sun produces in years. These giant flares create short gamma-ray bursts detectable across cosmic distances, brief but incredibly intense pulses of high-energy radiation. The physics involved defies everyday experience. A magnetar's magnetic field is so intense it would be lethal to humans at distances of thousands of kilometers, not from radiation, but from the magnetic field itself, so fly, which would interfere with the electrical activity in your nervous system. The field is strong enough to distort the shape of atoms, creating exotic states of matter that exist nowhere else in the universe except possibly in the cores of neutron stars. When magnetars flare, they briefly become the brightest objects in their local galactic neighborhoods. In December of 2004, a giant flare from magnetar SGR 1806-20 produced more energy in 1/10 of a second than our Sun will generate over 100,000 years. The burst was so intense it temporarily blinded gamma-ray satellites and caused detectable changes in Earth's ionosphere, despite originating 50,000 light-years away on the opposite side of our galaxy. Here's where the mathematics become genuinely unsettling. Computer models suggest that a magnetar giant flare, occurring within roughly 30 light-years of Earth, could strip away a significant portion of our planet's ozone layer, exposing the surface to lethal levels of ultraviolet radiation. At distances of 10 light-years or less, such an event might cause mass extinctions comparable to the worst episodes in Earth's geological record. Fortunately, we don't know of any magnetars in our immediate cosmic neighborhood. The nearest confirmed magnetar lies over 9,000 light-years away, uncomfortably close in galactic terms, but far enough that even a major outburst would pose no direct threat to Earth. However, neutron stars are notoriously difficult to detect unless they're actively emitting radiation, and astronomers estimate there could be billions of them scattered throughout our galaxy. Even more concerning are long gamma-ray bursts, the death screams of the most massive stars in the universe. When a star more than 25 times the mass of our Sun reaches the end of its life, it doesn't simply explode like an ordinary supernova. Instead, its core collapses directly into a black hole, launching jets of material at nearly the speed of light. These jets, focused into narrow beams by the extreme physics near the black hole's event horizon, create some of the most energetic explosions in the universe. The lethal distance for gamma-ray bursts depends critically on their energy and geometry, but atmospheric modelling suggests that a burst occurring within several thousand light-years of Earth and aimed directly at us could trigger significant ozone depletion and climate disruption. The burst itself would last only seconds to minutes, but its effects on Earth's atmosphere could persist for years. The terrifying aspect of gamma-ray bursts isn't just their energy output, it's their complete unpredictability. Unlike supernovae, which can sometimes be anticipated based on the properties of their progenitor stars, gamma-ray bursts appear to occur randomly throughout the universe, with no advance warning. The first indication of such an event would be the arrival of the gamma rays themselves, travelling at light speed and providing zero warning time. Modern gamma-ray astronomy has revealed that these cosmic catastrophes occur roughly once per day, somewhere in the observable universe. A sobering reminder of how violent and dangerous the cosmos really island. Fortunately, the beaming effects that make gamma-ray bursts so energetic also work in our favour. The jets are typically only a few degrees wide, meaning that even a relatively nearby burst would need to be aimed with extraordinary precision to affect Earth. The detection network monitoring these cosmic giants has grown increasingly sophisticated. NASA's Fermi Gamma Ray Space Telescope, the Swift Observatory, and ground-based gravitational wave detectors like LIGO, Virgo, and KEGRA work together to provide real-time alerts when these cosmic catastrophes occur. Within minutes of detecting a gamma-ray burst, astronomers worldwide can point optical and radio telescopes toward the source, capturing the afterglow and learning about the physics of stellar death. This multi-messenger approach has revolutionized our understanding of cosmic violence. We're no longer limited to studying these events through a single type of radiation. We can observe them through gravitational waves, gamma rays, optical light, and radio emissions simultaneously, building a complete picture of what happens when the universe unleashes its full fury. The frequency versus consequence relationship for these cosmic giants provides both comfort and concern. The most energetic events, those capable of affecting Earth from great distances, are also the rarest. Magnetard giant flares occur perhaps once per century in a typical galaxy. Nearby gamma-ray bursts capable of damaging Earth's biosphere are estimated to occur only once every few 100 million years. Yet the universe is vast, containing hundreds of billions of galaxies, each hosting billions of stars in various stages of their life cycles. Somewhere in the observable universe, neutron stars are colliding, magnetars are flaring, and massive stars are launching gamma-ray bursts toward unseen targets. The fact that we can detect these events from billions of light-years away is a testament both to their incredible energy and to the sophisticated instruments we've developed to study them. What makes these cosmic giants particularly unsettling is their role as cosmic arbiters of habitability. A sufficiently close and well-aimed gamma-ray burst could sterilize Earth's surface without warning, resetting the evolutionary clock and forcing any surviving life to begin again from the simplest organisms. In this sense, these stellar phenomena serve as a kind of cosmic quality control, periodically cleansing planets of complex life and ensuring that intelligence remains a rare and precious commodity in the universe. But what if the next brilliant flash across our sky isn't the collision of distant neutron stars, but something far more violent, a star's final, desperate scream as it tears itself apart in one last bid for immortality? Part 9. Hypothetical Doomsday 3. The False Dawn Star. Imagine waking one morning to find the eastern horizon ablaze with light that isn't the Sunday. A false dawn stretches across the sky, casting shadows in the wrong direction and painting the landscape in colours that have no name. For a few terrifying seconds, this alien sunrise outshines the real one, visible even in broad daylight before fading to a brilliant point of light that will haunt the sky for months to come. You've just witnessed the death of a massive star and the birth of one of the universe's most terrifying phenomena. This is our third hypothetical doomsday scenario, a nearby massive star collapsing into a black hole and firing a gamma-ray burst directly toward Earth. While the odds of such an event are extraordinarily small, the consequences would be so catastrophic that even seasoned astronomers occasionally lose sleep, contemplating the possibility. Gamma-ray bursts represent the universe at its most violent. When a star more than 25 times the mass of our Sun reaches the end of its life, its core can collapse so rapidly that not even a supernova explosion can halt the formation of a black hole. The infalling matter doesn't disappear quietly. It forms a superheated accretion disk around the newborn black hole, and launching jets of material at 99.9%, the speed of light along the star's rotation axis. These jets carry more energy than our Sun will produce over its entire 10 billion year lifetime, compressed into beams only a few degrees wide. When one of these cosmic death rays sweeps across space, it creates a gamma-ray burst, an explosion so bright it can be seen from the edge of the observable universe. The physics involved pushes the boundaries of what matter and energy can accomplish. The gamma rays themselves are photons carrying millions of times more energy than visible light. When they interact with Earth's atmosphere, they don't create a gentle aurora, they trigger nuclear reactions in the upper atmosphere, converting nitrogen and oxygen into radioactive isotopes and destroying the ozone molecules that protect us from the Sun's ultraviolet radiation. Computer models of this atmospheric destruction paint a sobering picture. A gamma-ray burst occurring within a few thousand light-years of Earth and aimed directly at us could deplete our ozone layer by 50% or more within seconds. The immediate effects would be invisible to human observers. Gamma rays don't create spectacular light shows when they hit our atmosphere, but within days or weeks the consequences would become apparent as increased levels of ultraviolet radiation began reaching Earth's surface. The biological impact would unfold over months to years. Without adequate ozone protection, ultraviolet radiation would penetrate deeper into the ocean, disrupting phytoplankton populations that form the base of marine food chains. On land, increased UV levels would cause widespread DNA damage in plants and animals, leading to increased cancer rates, immune system suppression, and agricultural failures. The most vulnerable ecosystems, those already stressed by climate change or human activity, would face potential collapse. But here's where the story becomes particularly unsettling. There would be no warning. Unlike asteroid impacts, which we might detect months or years in advance, gamma-ray bursts travel at the speed of light. The first indication of such an event would be the arrival of the gamma rays themselves. Satellite-based gamma-ray detectors would register the burst within milliseconds, but by then the damage to Earth's atmosphere would already be underway. The false dawn effect would be genuinely terrifying for any humans witnessing it. For a few seconds to minutes, a gamma-ray burst occurring within our galactic neighborhood would appear as a brilliant new star, potentially brighter than the full moon. Ancient astronomers would have interpreted such an event as a divine omen. Modern observers would know immediately that they were witnessing something unprecedented and potentially catastrophic. Historically, astronomers have worried about several candidate stars that might pose such a threat. Wolf-Rayet 104, a massive star roughly 8,000 light-years away, once topped lists of most likely to kill us all due to its enormous mass and rapid rotation. However, more recent observations have suggested that its rotation axis isn't aligned with Earth, meaning any gamma-ray burst it produces would likely miss us entirely. This raises a crucial point about gamma-ray burst geometry. The beaming effect that makes these explosions so energetic also works in our favour. The jets are typically only 1 to 10 degrees wide, meaning that even a relatively nearby massive star would need to be oriented with extraordinary precision to pose a direct threat to Earth. Most gamma-ray bursts sweep through empty space, their deadly radiation dissipating harmlessly into the cosmic void. The timescales involved in gamma-ray burst effects span from seconds to centuries. The initial burst itself typically lasts anywhere from milliseconds to several minutes, a brief but incredibly intense pulse of high-energy radiation. The atmospheric chemistry effects would peak within days but could persist for months or years as the depleted ozone layer slowly recovered. Biological and ecological consequences might unfold over decades or centuries. Current estimates suggest that potentially lethal gamma-ray bursts occur in our galactic neighborhood roughly once every few 100 million years, frequent enough to have influenced the course of life on Earth over geological time, but rare enough that human civilization is unlikely to experience such an event. Some researchers have even proposed that gamma-ray bursts might explain certain mass extinction events in Earth's geological record, though the evidence remains speculative. The detection and monitoring of massive stars has become increasingly sophisticated as astronomers have come to understand the gamma-ray burst threat. Space-based telescopes continuously monitor known Wolf-Rayet stars and other gamma-ray burst candidates, looking for signs of instability that might herald an impending collapse. Ground-based surveys search for new candidates, while theoretical models attempt to predict which stars are most likely to produce Earth-threatening bursts. Yet even with improved monitoring, the fundamental unpredictability of stellar collapse means that gamma-ray bursts will always retain an element of cosmic roulette. We can identify the most likely candidates, but we cannot predict when, or if, they will explode. We can model the atmospheric effects with increasing precision, but we cannot prevent them from occurring. The psychological impact of living with this knowledge is worth considering. How does it feel to know that somewhere in our galaxy, massive stars are approaching the end of their lives, potentially carrying within them the power to reset civilization? For most people, such threats remain comfortably abstract, too rare and unpredictable to influence daily decision-making. But for astronomers who study these phenomena professionally, the knowledge can be genuinely unsettling. Perhaps the most disturbing aspect of the gamma-ray burst scenario is its reminder of how little control we have over cosmic phenomena operating on scales far beyond human influence. We've developed impressive capabilities for detecting and potentially deflecting asteroid threats. We've mapped the locations of nearby black holes and monitored the activity of our galactic center. But against a well-aimed gamma-ray burst, our technological civilization would be as helpless as the dinosaurs were against their cosmic impactor. The silver lining, if it can be called that, lies in the rarity and randomness of such events. The universe contains billions of massive stars, but only a tiny fraction will ever produce gamma-ray bursts, and an even smaller fraction will aim those bursts toward inhabited planets. The cosmic lottery that governs stellar death appears to be rigged in favor of survival most of the time. But what if the next existential threat doesn't come from exploding stars or colliding neutron stars? What if it emerges from the fundamental structure of reality itself, a wave of destruction that rewrites the laws of physics as it passes? Part 10. Hypothetical Doomsday 4. The Cosmic Wave. In the realm of speculative cosmic catastrophes, few scenarios are as simultaneously fascinating and terrifying as the possibility of a cosmic wave, a hypothetical disturbance in the fabric of space itself that could fundamentally alter the laws of physics as we know them. This is our fourth and most exotic doomsday scenario, a thought experiment that pushes the boundaries of theoretical physics into territory that would make even science fiction writers pause. Let's be absolutely clear from the start. There is no credible scientific evidence suggesting that such cosmic waves exist or pose any threat to Earth. The scenario we're about to explore exists purely in the realm of speculative physics and worst-case theoretical modeling. But the very fact that reputable physicists have seriously considered such possibilities tells us something profound about how much we still don't understand about the universe we inhabit. The concept emerges from our growing awareness of dark energy, the mysterious force that appears to be accelerating the expansion of the universe. When Albert Einstein first introduced his cosmological constant in 1917, he intended it as a static fudge factor to keep the universe from collapsing under its own gravity. He later called it his greatest mistake, when observations revealed that the universe was actually expanding. But in 1998, astronomers discovered that this expansion is accelerating, driven by some form of energy that permeates all of space. Dark energy represents roughly 68% of the total mass energy content of the universe, yet we understand almost nothing about its true nature. Is it a fundamental property of space itself? Is it a field that could potentially change strength or direction? Could it be unstable under certain conditions? These questions push us into uncharted theoretical territory, where even our most sophisticated models provide little guidance. One speculative possibility that occasionally surfaces in theoretical literature is the concept of a false vacuum decay, the idea that the quantum fields that define the fundamental properties of matter and energy might exist in a metastable state, like a ball balanced on the rim of a bowl rather than resting at the bottom. If such a system were disturbed, perhaps by quantum fluctuations or interactions with other fields we haven't yet discovered, it could theoretically trigger a cascade effect that would propagate outward at the speed of light. Such a wave wouldn't be made of matter or conventional energy. It would represent a fundamental change in the underlying structure of space-time itself, a region where the laws of physics operating behind the wavefront would be fundamentally different from those we observe today. Atoms might not be able to form. The fundamental forces might operate with different strengths. The very concept of matter as we understand it might cease to have meaning. The terrifying aspect of such a scenario isn't the energy involved, it's the complete unpredictability of what would happen when the wave arrived. Would matter simply cease to exist? Would it transform into exotic forms governed by alien physics? Would conscious observers even be capable of perceiving the transition, or would awareness itself be impossible under the new physical regime? Fortunately, the same physics that makes such scenarios theoretically possible also suggests they're extraordinarily unlikely to occur naturally. Quantum field theory indicates that false vacuum decay events, if they occur at all, would be incredibly rare, perhaps once per universe per cosmic age. The energy barriers protecting our current vacuum state appear to be enormous, requiring fluctuations far more extreme than anything our current models predict. Moreover, our local observations of the cosmic microwave background radiation, the afterglow of the Big Bang, show no signs of the kind of irregularities that might indicate vacuum instability. The universe appears to be operating under consistent physical laws across billions of light-years of space and billions of years of time. If our vacuum state were genuinely unstable, we might expect to see evidence of decay events occurring in distant regions of the observable universe. The concept of cosmic waves also intersects with our understanding of the cosmic web, the large-scale structure of the universe revealed by galaxy surveys and computer simulations. On scales of hundreds of millions of light-years, matter is organized into filaments and sheets separated by vast voids. Shock waves and pressure fronts propagate through this cosmic web as galaxy clusters collide and merge. But these are conventional phenomena involving the movement of gas and dark matter, not fundamental changes to the laws of physics. Some speculative theories in cosmology do allow for more exotic possibilities. Brain-world scenarios suggest that our entire universe might exist as a membrane embedded in a higher dimensional space, potentially subject to collisions or interactions with other brains that could fundamentally alter physical laws. String theory landscapes propose vast arrays of possible vacuum states, each with different physical constants and particle properties. But here's where scientific responsibility becomes crucial. The boundary between legitimate theoretical speculation and unfounded fear-mongering can be surprisingly thin. The internet is filled with claims about imminent cosmic wave threats, based on misinterpretations of legitimate scientific papers or complete fabrications designed to generate clicks and views. Distinguishing between peer-reviewed theoretical work and YouTube cosmology requires careful attention to sources and methodology. The scientific community has developed several ways to test the stability of our current vacuum state. Particle accelerators like the Large Hadron Collider probe the behavior of fundamental fields at high energies, looking for signs of instability or phase transitions. Cosmological observations monitor the cosmic microwave background and large-scale structure for anomalies that might indicate vacuum decay events elsewhere in the universe. So far, all observations suggest that our universe is operating under stable physical laws that have remained consistent across cosmic time. The fundamental constants appear to be truly constant. The quantum fields that define particle masses and interaction strengths show no signs of instability or decay. If cosmic waves of the type we've been imagining exist at all, they operate on timescales and distance scales that dwarf human civilization. The psychological impact of contemplating such scenarios is worth acknowledging. There's something uniquely disturbing about threats that attack the very foundation of physical reality, rather than simply destroying matter or energy within the current framework. We can imagine surviving asteroid impacts, radiation exposure, even climate change, but it's difficult to conceive of existence itself under fundamentally different physical laws. Yet this discomfort also points to something positive about human nature, our deep confidence in the stability and comprehensibility of the universe around us. The fact that cosmic wave scenarios feel so alien and threatening suggests that we've evolved in a genuinely stable cosmic environment, one where the laws of physics have remained consistent long enough for complex structures like galaxies, stars, planets, and life to emerge and persist. The ultimate lesson of cosmic wave speculation might be one of cosmic humility. Despite centuries of scientific progress, we still understand only a fraction of what governs the universe at its deepest levels. Dark energy remains a mystery. Quantum gravity eludes our best theoretical efforts. The relationship between consciousness and physical law remains completely opaque. But perhaps that's exactly why we should be grateful rather than terrified. The universe has provided us with a stable platform for existence, discovery, and wonder. The laws of physics have remained consistent long enough for intelligence to emerge and begin asking questions about its own existence. Whatever cosmic waves might theoretically exist in the vast spaces between galaxies, they haven't yet reached our corner of space-time. In the end, the most honest response to cosmic wave scenarios is not fear, but awe at the complexity and subtlety of the universe we inhabit, and gratitude for the remarkable stability that has allowed us to exist long enough to contemplate our own cosmic situation. If the universe were truly unstable at fundamental levels, we wouldn't be here to worry about it. But if the fabric of space-time isn't hunting us, and if the laws of physics remain stable and benevolent, perhaps the greatest threats to our survival come not from hostile cosmos, but from other forms of intelligence that have learned to navigate cosmic dangers far better than we have. Part 11. The Fermi Paradox. In 1950, during a casual lunch conversation at Los Alamos National Laboratory, physicist Enrico Fermi posed a question that continues to haunt astronomers and philosophers today. Where is everybody? His reasoning was deceptively simple. The universe is roughly 13.8 billion years old and contains hundreds of billions of galaxies, each hosting hundreds of billions of stars. Even conservative estimates suggest that billions of planets should be capable of supporting life. So, where are all the aliens? This apparent contradiction between the high probability of extraterrestrial intelligence and our complete lack of evidence for it has become known as the Fermi Paradox. It's not really a paradox in the mathematical sense. It's more of a profound puzzle that forces us to confront uncomfortable possibilities about our place in the cosmic order. Are we alone? Are we early? Are we being avoided? Or are we simply looking in the wrong places with the wrong tools? The numbers involved are staggering. Our galaxy alone contains roughly 400 billion stars, and recent discoveries by the Kepler Space Telescope and other planet-hunting missions suggest that Earth-sized planets in the habitable zones of their stars are surprisingly common. Conservative estimates indicate that there could be billions of potentially habitable worlds in the Milky Way alone. Expand that to the observable universe, with its estimated 2 trillion galaxies, and the numbers become almost meaningless in their immensity. Yet despite decades of searching, we've found no definitive evidence of extraterrestrial intelligence, no radio signals that couldn't be explained by natural phenomena, no megastructures blocking the light of distant stars, no obvious signs of industrial activity in nearby star systems. The universe appears to be conspicuously quiet, a cosmic library with no other readers. The silence takes on 2 distinct flavors, each with its own troubling implications. First, there's the absence of visitation, the fact that no alien spacecraft have landed on the White House lawn, despite what tabloid headlines might suggest. Second, and perhaps more puzzling, is the absence of detectable signals or signatures of technological civilization anywhere in our cosmic neighborhood. Our search capabilities, while impressive by historical standards, remain quite limited. The Search for Extraterrestrial Intelligence project has examined only a tiny fraction of nearby stars, and only within narrow frequency bands that we assume might be favored for interstellar communication. We're essentially trying to eavesdrop on cosmic conversations using techniques barely more sophisticated than those available to Marconi at the dawn of radio. Advanced civilizations might communicate using methods we haven't even imagined yet. The temporal dimension of the Fermi paradox adds another layer of complexity. Human civilization has been technologically advanced for only a few centuries, a cosmic eye blink. Radio astronomy has existed for less than a century. We've been actively searching for extraterrestrial signals for only a few decades. If technological civilizations are short-lived, lasting only centuries or millennia before destroying themselves or transcending their technological phase, the chances of 2 civilizations overlapping in both space and time become vanishingly small. Consider the vast scales involved. Light from the nearest star takes over 4 years to reach us. A radio signal from the galactic, the center would require 26,000 years to cross the space between there and here. If an alien civilization had been broadcasting a "Hello Universe" message when the Egyptian pyramids were being built, that signal would just now be reaching star systems 5,000 light-years away. The universe operates on timescales that make civilizational overlap seem almost impossible. This leads to what researchers call the Great Filter hypothesis, the idea that there's some evolutionary or technological barrier that prevents most life from developing into detectable, spacefaring civilizations. The filter might be behind us, perhaps the emergence of life itself, or the development of complex cells, or the evolution of intelligence is far rarer than we assume. Alternatively, the filter might lie ahead, Perhaps technological civilizations inevitably destroy themselves through war, environmental collapse, or other catastrophes before they become detectable on cosmic scales. The possibility that the Great Filter lies ahead of us is particularly unsettling. If intelligence inevitably leads to self-destruction, then our current technological capabilities might represent not the beginning of a cosmic conversation, but the final chapter of terrestrial intelligence. Every nuclear weapon we build, every degree of warming we add to our climate, every potentially dangerous technology we develop could be steps toward the same fate that has silenced countless other civilizations. But there are other possibilities that don't require assuming civilizational suicide. Perhaps advanced civilizations deliberately choose to remain quiet, recognizing that announcing their presence might attract unwanted attention from hostile neighbors. Perhaps they've transcended the need for electromagnetic communication, developing technologies that operate through quantum entanglement or other phenomena we've barely begun to understand. Perhaps they're already here, observing us with such sophisticated camouflage that we can't detect their presence. The search strategies employed by modern SETI research have evolved far beyond simply listening for radio signals. Astronomers now look for technosignatures, indirect evidence of technological activity that might be visible across interstellar distances. These include searches for artificial structures that might partially block the light from stars, analysis of exoplanet atmospheres for industrial pollutants, and monitoring for brief laser pulses that might represent interstellar communication attempts. The recent focus on fast radio bursts, mysterious millisecond pulses of radio energy from distant galaxies, illustrates both the promise and the frustration of modern SETI work. When these signals were first discovered, some researchers speculated they might represent alien technology. More detailed analysis has revealed they're almost certainly natural phenomena, likely produced by highly magnetized neutron stars called magnetars. But the fact that we seriously considered artificial origins shows how desperately we want to find evidence that we're not alone. Our bias toward anthropocentric thinking might be limiting our search strategies. We look for the kinds of signals we might send, using the technologies we understand, operating on the timescales that seem reasonable to us. But advanced civilizations might communicate using gravitational waves, manipulate matter at the quantum scale, or operate on geological timescales that make our entire recorded history seem like a brief moment of noise. The Drake equation, formulated in 1961 to estimate the number of communicating civilizations in our galaxy, remains more of a philosophical framework than a predictive tool. Its variables, the rate of star formation, the fraction of stars with planets, the likelihood of life emerging, are still poorly constrained despite decades of astronomical progress. Depending on which estimates you plug into the equation, you can derive results ranging from "we're probably alone in the universe" to "there should be millions of detectable civilizations." Perhaps the most profound implication of the Fermi paradox isn't about aliens at all, it's about us. The apparent silence of the universe places an enormous responsibility on human civilization. If intelligence is as rare as the evidence suggests, then we might represent something genuinely precious in the cosmic order, a brief flowering of consciousness in an otherwise unconscious universe. This responsibility cuts both ways. On one hand, it suggests that human civilization and the intelligence it represents might be worth preserving at almost any cost. On the other hand, it raises the terrifying possibility that we're approaching the same filter that silenced all those other potential civilizations. Every global crisis we face, climate change, nuclear proliferation, artificial intelligence development, biotechnology risks, takes on cosmic significance when viewed through the lens of the Fermi paradox. The paradox also forces us to confront the possibility that consciousness itself might be far rarer and more fragile than we instinctively assume. We take our own awareness for granted, but the emergence of subjective experience from complex information processing remains one of science's deepest mysteries. If consciousness is indeed rare in the universe, then its preservation becomes a cosmic imperative. Recent developments in astrobiology have added new dimensions to the Fermi paradox. The discovery of potentially habitable exoplanets like Proxima Centauri b, TRAPPIST-1e, and Kepler 452b has shown that Earth-like worlds exist in our cosmic neighborhood. The James Webb Space Telescope's ability to analyze exoplanet atmospheres will soon tell us whether any of these worlds show signs of biological activity. But even if we find life, the question of intelligence will remain. The search for extraterrestrial intelligence continues to evolve and expand. New radio telescope arrays like the Square Kilometre Array will provide unprecedented sensitivity to artificial signals. Optical SETI searches monitor millions of stars for brief laser pulses. The Breakthrough Listen initiative has brought Silicon Valley funding and expertise to the search for cosmic companions. Yet with each passing year of silence, the Fermi paradox becomes more puzzling rather than less. Either we're extraordinarily alone, extraordinarily early, or extraordinarily blind to the signs of intelligence around us. Each possibility carries profound implications for how we understand our place in the universe and our responsibility to the future. But what if the silence itself is the answer? What if advanced civilizations have learned that the universe is far more dangerous than it appears, and that survival requires something we haven't yet mastered, the discipline of cosmic invisibility? Part 12. The Dark Forest Hypothesis. In Liu Cixin's acclaimed science fiction trilogy, The Three-Body Problem, humanity's first contact with extraterrestrial intelligence comes with a chilling warning: do not answer, do not answer, do not answer. The message comes from an alien pacifist desperately trying to prevent Earth from revealing its location to a galaxy full of predators. This fictional scenario encapsulates one of the most unsettling proposed solutions to the Fermi paradox, the Dark Forest Hypothesis. Named after the second volume in Liu's trilogy, the Dark Forest Hypothesis suggests that the universe is indeed teeming with intelligent civilizations, but they all remain silent out of an abundance of caution. Like hunters moving carefully through a dark forest, each civilization knows that others exist but dares not reveal its own position, because the first rule of cosmic survival is simple: any civilization capable of interstellar travel is also capable of interstellar destruction. The logic is coldly game theoretic. When two civilizations encounter each other across interstellar distances, each faces a fundamental uncertainty about the other's intentions. Even if the alien civilization appears peaceful, there's no way to guarantee that it will remain so across the centuries or millennia required for meaningful interstellar interaction. Technological capabilities grow exponentially, and a civilization that poses no threat today might develop planet-killing weapons tomorrow. Moreover, there's no reliable way to communicate peaceful intentions across interstellar distances. Any signal strong enough to cross space could also serve as a targeting beacon. Any technology capable of propelling spacecraft to other stars could also propel weapons. In this framework, the safest assumption is that any detected civilization represents a potential existential threat that should be eliminated before it can eliminate you. This creates what researchers call a cosmic Cold War, a universe where every civilization capable of interstellar travel maintains strict operational security, monitoring for signs of other civilizations while revealing as little as possible about themselves. Detection equals death, so survival requires perfect stealth across cosmic timescales. The hypothesis gains unsettling credibility when we consider Earth's own behavior. For the past century, we've been inadvertently broadcasting our presence to the galaxy through radio and television transmissions, radar signals, and other electromagnetic radiation. Our planet glows like a beacon in certain radio frequencies, announcing to anyone listening that Earth hosts a technological civilization. But are we wise to be so conspicuous? The debate over METI, messaging to extraterrestrial intelligence, illustrates the tensions inherent in the dark forest scenario. Since the 1970s, humans have occasionally transmitted deliberate messages toward nearby star systems, including mathematical concepts, cultural information, and even musical compositions. The Arecibo message, broadcast in 1974 toward the globular cluster M13, will arrive at its destination in roughly 25,000 years. Critics of METI argue that we're essentially sending our cosmic address to unknown recipients who might not have our best interests at heart. Proponents counter that our inadvertent radio leakage has already announced our presence, so deliberate messaging adds little additional risk. But the dark forest hypothesis suggests that both perspectives might be dangerously naive, that in a universe full of hidden civilizations, any form of conspicuous behavior could be suicidal. The mathematics of interstellar warfare support these grim calculations. A civilization capable of accelerating spacecraft to significant fractions of light speed possesses the technology to deliver kinetic weapons with devastating effect. A simple probe traveling at 10% of light speed would impact with the energy of thousands of nuclear weapons. At relativistic speeds, even small objects become planet killers. Detection technologies follow similar exponential curves. A civilization capable of building radio telescopes much larger than our current instruments could detect Earth's broadcast emissions from hundreds of light years away. More advanced civilizations might monitor gravitational waves, neutrino emissions, or exotic signatures we haven't even imagined. In the dark forest scenario, the watchers are always ahead of the watched. The hypothesis also explains several puzzling aspects of the Fermi paradox. Why don't we see obvious signs of galactic engineering or megastructure construction? Because civilizations that build conspicuous monuments to their technological prowess don't survive long enough to become galactic civilizations. Why don't we detect industrial waste heat or atmospheric pollution on exoplanets? Because advanced civilizations either hide their signatures or eliminate civilizations that fail to hide theirs. Even more disturbing is the possibility that Earth is already being observed by hidden civilizations that are waiting to see what we become. In this scenario, our planet represents a kind of cosmic exam, a test of whether human civilization can mature into a responsible galactic citizen, or whether we'll follow the path of aggressive expansion that characterizes most failed civilizations. The recent focus on interstellar objects like Oumuamua takes on sinister overtones when viewed through the dark forest lens. While mainstream astronomy treats these visitors as natural phenomena, comets or asteroids from other star systems, the hypothesis suggests they might represent something far more ominous: scout probes from civilizations monitoring our development. Their unusual characteristics, including Oumuamua's non-gravitational acceleration and cylindrical shape, would be consistent with artificial objects designed for reconnaissance. Similarly, the growing catalogue of unexplained atmospheric phenomena, including the military's acknowledgement of unidentified aerial phenomena that exhibit flight characteristics beyond current human technology, might represent evidence that we're already being studied by civilizations following dark forest protocols. They observe but don't interact, gathering intelligence while maintaining plausible deniability. The implications for human behavior are profound. If the dark forest hypothesis is correct, then our species faces a stark choice: learn cosmic stealth and join the galactic community of hidden civilizations, or continue broadcasting our presence and risk elimination by more cautious neighbors. The window for making this choice might be narrower than we think. Other civilizations might interpret our current level of radio emissions as evidence that we're too immature or reckless to be allowed to develop interstellar capabilities. Some researchers have proposed that humanity should immediately cease all high-power radio transmissions and implement planetary radio discipline to reduce our electromagnetic signature. Others argue that it's already too late, that our radio emissions from the past century have created an expanding sphere of detectability that now encompasses hundreds of nearby star systems. The psychological impact of accepting the dark forest hypothesis is genuinely unsettling. It suggests that the universe is not a vast empty stage waiting for cosmic civilization to flourish, but a dark ocean teeming with predators where the slightest disturbance can attract fatal attention. Every radio telescope we build, every deep space probe we launch, every attempt to contact extraterrestrial intelligence becomes a potential death warrant for our species. Yet the hypothesis also offers a strange form of hope. If it's correct, then the universe is indeed full of intelligent life. We're just not allowed to see it until we prove ourselves worthy of membership in the galactic community. The silence we observe might not represent cosmic loneliness, but cosmic discipline. A universe full of civilizations that have learned the hardest lesson of all. Sometimes, survival requires invisibility. The question that keeps astronomers awake isn't whether other civilizations exist, it's whether they've learned to hide so well that we'll never find them. And more troubling still, have they already found us? Part 13: Alien Conspiracies and Hidden Visitors. The line between legitimate scientific inquiry and conspiracy theory has never been thinner than it is today when discussing the possibility of hidden alien visitors in our solar system. Recent years have brought a perfect storm of genuinely puzzling astronomical discoveries, official government acknowledgements of unexplained phenomena, and an internet ecosystem that amplifies speculation faster than peer review can sort fact from fiction. Consider the case of Oumuamua, the first confirmed interstellar object to visit our solar system. When astronomers discovered this cigar-shaped visitor in 2017, it initially appeared to be a straightforward, if exciting, example of natural debris from another star system. But as observations accumulated, Oumuamua began displaying behavior that challenged conventional explanations. Most troubling was its non-gravitational acceleration. The object was speeding up in ways that couldn't be explained by the gravitational influences of the Sun and planets alone. For natural comets, such acceleration is routine, caused by jets of vaporizing ice that create tiny rocket effects. But Oumuamua showed no signs of the gas and dust clouds that typically accompany active comets. It was accelerating like a comet while looking like an asteroid. Into this gap between observation and explanation stepped some genuinely speculative ideas. Harvard astronomer Avi Loeb proposed that Oumuamua might represent artificial technology, specifically a light sail pushed by radiation pressure from the Sunday. His calculations showed that an object with the right geometry and composition could indeed exhibit Oumuamua's observed acceleration through purely artificial means. The scientific community's response was swift and largely skeptical. Alternative explanations emerged. Perhaps Oumuamua was composed of solid hydrogen that sublimated invisibly, or maybe it was a fragment of a disrupted planet with unusual thermal properties. The European Space Agency's official analysis concluded that natural outgassing remained the most plausible explanation, even if the gas wasn't visible in Earth-based telescopes. Yet the controversy surrounding Oumuamua illustrates a broader challenge in modern astronomy. How do we distinguish between genuinely anomalous phenomena that deserve serious investigation and sensationalized claims that mistake natural processes for artificial intelligence? The answer lies in the quality and quantity of evidence, the rigor of analysis, and the willingness to accept mundane explanations even when exotic alternatives might seem more exciting. 2 years after Oumuamua's departure, the solar system received another interstellar visitor, Comet Borisov. This object behaved exactly as astronomers expected, displaying a normal coma and tail, outgassing at predictable rates, and following a trajectory consistent with natural gravitational mechanics. Borisov served as a perfect control experiment, demonstrating that interstellar objects can and do behave according to well-understood physics. The arrival of 3I-ATLAS in 2025 has renewed these debates. Like Oumuamua, this latest interstellar visitor has generated its share of speculation, particularly regarding its green coloration. Social media posts have breathlessly described it as an alien craft or extraterrestrial probe, but the reality is far more prosaic. That eerie green glow almost certainly comes from the same diatomic carbon fluorescence that colors many ordinary comets, a natural phenomenon caused by solar radiation energizing simple molecules in the object's coma. The challenge for both scientists and the public is maintaining appropriate skepticism while remaining open to genuinely revolutionary discoveries. The universe is vast and strange, and it's entirely possible that some astronomical phenomena might eventually prove to be artificial in origin. But extraordinary claims require extraordinary evidence, and that evidence must meet rigorous scientific standards. This becomes particularly important when we consider how alien visitation claims proliferate in the digital age. A single unusual observation can spawn dozens of YouTube videos, blog posts, and social media threads, each amplifying speculative interpretations while often ignoring more mundane explanations. The result is a kind of information ecosystem where sensational claims spread faster than careful analysis can debunk them. The recent military acknowledgement of unidentified aerial phenomena, objects displaying flight characteristics that exceed known human technology, has added another layer of complexity to these discussions. While defense officials have been careful to avoid claiming these phenomena are extraterrestrial in origin, the mere admission that military sensors have detected objects behaving in inexplicable ways has energized speculation about hidden alien presence on Earth. If extraterrestrial civilizations were conducting surveillance of Earth, what would that surveillance look like? The dark forest hypothesis suggests that advanced civilizations would prioritize stealth above all else, using technology so sophisticated that their probes would be essentially undetectable by primitive civilizations like ours. Such probes might masquerade as natural objects, asteroids, comets, or even mundane space debris, while gathering intelligence about human technological development. The physics of interstellar probe design supports this possibility. A sufficiently advanced civilization could construct surveillance devices small enough to avoid easy detection, while powerful enough to monitor an entire planet's electromagnetic emissions. These probes might be entirely passive, collecting data without transmitting anything that could reveal their artificial nature. They could remain in our solar system for decades or centuries, studying human civilization while remaining completely hidden. From this perspective, every unusual astronomical object becomes potentially suspicious. Could some near-Earth asteroids be disguised alien artifacts? Might some comets be carrying hidden sensors along with their natural ice and rock? Are there monitoring stations hidden among the Trojans at Jupiter's Lagrange points, or camouflaged as ordinary Kuiper belt objects in the outer solar system? The uncomfortable truth is that current astronomical surveys aren't designed to detect such objects, even if they exist. We catalogue asteroids and comets based on their orbits and basic physical properties, but we rarely examine them in the kind of detail that might reveal artificial components. A sufficiently sophisticated probe could easily hide among the millions of small bodies in our solar system, indistinguishable from natural debris until subjected to close inspection. This creates a troubling epistemic problem. Absence of evidence isn't evidence of absence. The fact that we haven't definitively detected alien probes in our solar system doesn't prove they're not there. It might simply mean they're better at hiding than we are at seeking. Every natural explanation for unusual phenomena like Oumuamua's acceleration might be correct, but it might also represent successful camouflage by intelligence far more advanced than our own. The implications extend beyond pure science into questions of planetary security and human autonomy. If Earth is indeed under surveillance by hidden extraterrestrial intelligence, what are the Watchers learning about us? Are they studying our technology, our biology, our social structures? Are they simply gathering data, or are they preparing for some form of contact or intervention? These questions resist easy answers because they operate at the intersection of legitimate scientific inquiry and unavoidable speculation. The tools of science work well for studying natural phenomena that follow consistent physical laws, but they're less effective at detecting intelligence that might be actively trying to avoid detection. We're essentially playing a cosmic game of hide-and-seek, where we don't know the rules, the number of players, or even whether the game is actually being played. The responsible approach lies in continued rigorous observation, combined with healthy skepticism about exotic explanations. Every anomalous object deserves careful study, but extraordinary claims require extraordinary evidence. The universe is strange, enough without invoking alien intelligence to explain every puzzling observation. Yet we should also remember that the absence of confirmed extraterrestrial visitors doesn't mean we're necessarily alone. The galaxy might be full of civilizations that are simply better at staying hidden than we are at finding them. In a universe governed by dark forest logic, the most successful civilizations might be the ones we never see at all. But what if some signals are so strange, so persistent, so clearly artificial in origin that natural explanations begin to strain credibility? What happens when the universe refuses to stay silent? Part 14. Things that don't add up. In the catalogue of cosmic mysteries that refuse to yield to conventional explanation, few phenomena have generated as much excitement and frustration as fast radio bursts. These millisecond duration flashes of radio energy, first discovered in archived data from 2007, seem to arrive from random directions in space, with no obvious natural explanation. For years, they represented one of astronomy's most tantalizing puzzles, brief, brilliant, and utterly alien. The mystery began with a single burst detected in data from the Parkes radio telescope in Australia, lasting only 5 milliseconds, but releasing as much energy and radio waves as the Sun produces in an entire day. The signal appeared to come from a galaxy billions of light-years away. Its frequency characteristics suggested it had travelled through vast amounts of ionized gas, confirming its extragalactic origin, but providing no clues about what could produce such an intense, brief flash of radio energy. For years, fast radio bursts existed in a kind of scientific limbo. Were they natural phenomena involving exotic stellar processes? Were they instrumental artifacts or terrestrial interference, masquerading as cosmic signals? Or could they represent something genuinely artificial, perhaps the signatures of advanced civilizations using focused radio beams for interstellar communication or propulsion? The artificial intelligence hypothesis gained traction among some researchers for compelling reasons. The burst's extreme brightness and brief duration seemed more consistent with engineered signals than natural processes. Their apparent random distribution across the sky suggested they might originate from many different sources rather than a single type of cosmic object. Most intriguingly, some bursts appeared to repeat, which seemed difficult to reconcile with catastrophic stellar events, but consistent with technology that could be activated multiple times. Then, in 2020, the mystery received its first major breakthrough. A fast radio burst was detected coming from within our own galaxy, specifically from SGR 1935 plus 2154, a known magnetar located roughly 30,000 light-years from Earth. This single observation revolutionized the field, proving conclusively that at least some fast radio bursts have natural origins. Magnetars are neutron stars with magnetic fields trillions of times stronger than Earth's, objects so extreme they exist at the very limits of what matter can withstand. When these stellar remnants experience starquakes, fractures in their incredibly dense crusts, they can release more energy in milliseconds than our Sun produces in years. The magnetic fields channel this energy into focused beams that sweep across space like cosmic lighthouses. The galactic fast radio burst wasn't just a scientific vindication of natural explanations, it was also a sobering reminder of the universe's capacity for violence. The energy release was so intense it temporarily disrupted Earth's ionosphere, despite originating 30,000 light-years away. If a similar event had occurred within a few hundred light-years of Earth, it might have caused significant damage to our technological infrastructure and potentially to our biosphere. But the Prezio-Roux magnetar explanation, while compelling for many fast radio bursts, doesn't solve every mystery. The population of observed bursts shows remarkable diversity in their properties. Some repeat, others are one-time events. Some show complex frequency structures, others are relatively simple. Some appear to come from active star-forming regions, others from apparently empty space. This diversity suggests that multiple physical processes might be responsible for creating these cosmic flashes. The story becomes even more complex when we consider other persistent cosmic anomalies that continue to defy easy explanation. The famous WOW signal, detected by the Big Ear radio telescope in 1977, remains one of astronomy's greatest unsolved mysteries. Lasting 72 seconds and displaying characteristics consistent with an artificial origin, the signal appeared once and was never detected again, despite decades of follow-up observations. Recent attempts to explain the WOW signal have focused on rare natural phenomena, perhaps the reflection of Earth-based radio emissions off a cloud of hydrogen atoms, or emissions from a comet whose hydrogen coma was unusually dense. But these explanations remain speculative, and the signal's precise frequency, duration, and failure to repeat continue to puzzle researchers more than 4 decades after its detection. Similarly, KIC 8462852, better known as Tabby's star, created a sensation in the astronomical community when citizen scientists discovered its bizarre pattern of brightness variations. The star would randomly dim by up to 22%, far more than could be explained by typical stellar processes or planetary transits. Initial speculation focused on alien megastructures, perhaps massive solar collectors or habitat rings constructed by an advanced civilization. Subsequent observations have largely deflated the alien megastructure hypothesis. The star's dimming appears to be wavelength dependent, which suggests dust or debris rather than solid structures. The most likely explanation involves clouds of comet fragments or asteroid debris periodically blocking the star's light. But the precise mechanism remains unclear, and Tabby's star continues to behave in ways that challenge our understanding of stellar systems. These cases illustrate both the promise and the peril of anomaly-driven astronomy. Unusual observations often point toward genuinely new physics or previously unknown astrophysical processes. The discovery of pulsars in 1967 initially generated speculation about artificial little green men signals before revealing the existence of neutron stars, objects so extreme they had been considered theoretically impossible. Similarly, gamma-ray bursts were mysterious for decades before we understood they represented the most violent explosions in the universe since the Big Bang. The challenge lies in distinguishing between genuinely revolutionary discoveries and more mundane phenomena masquerading as cosmic mysteries. Our pattern-seeking brains are exquisitely adapted to finding signals in noise, but this same capability can lead us to see artificial intelligence where only natural processes exist. The key is maintaining what Carl Sagan called the fine line between skepticism and wonder, remaining open to extraordinary discoveries while demanding extraordinary evidence. Modern surveys like the Zwicky Transient Facility and the upcoming Vera Rubin Observatory promise to revolutionize our ability to detect and study cosmic anomalies. By monitoring millions of stars simultaneously, these facilities will catch rare events that previous surveys might have missed. Computer algorithms will automatically flag unusual behavior, allowing astronomers to respond quickly with follow-up observations. But this flood of new data will also present new challenges. Every survey that becomes more sensitive discovers new types of COPS, transient phenomena, most of them natural, but some potentially artificial. Distinguishing between the two will require not just better instruments, but better theoretical frameworks for understanding what kinds of signatures advanced civilizations might produce. The search for genuine technosignatures, unambiguous evidence of extraterrestrial technology, continues to evolve beyond simple radio signals. Astronomers now monitor for infrared excess that might indicate Dyson spheres, look for laser pulses in optical data, and search for artificial transit patterns that might reveal megastructures. Each new survey technique opens possibilities for both discovery and disappointment. Perhaps most importantly, these cosmic anomalies remind us that the universe still holds profound mysteries that resist easy categorization. Whether they ultimately prove to be natural phenomena or something more exotic, they represent genuine puzzles that push the boundaries of our understanding. In a cosmos that can produce neutron stars, black holes, and dark energy, perhaps we shouldn't be surprised that some phenomena continue to challenge our theoretical frameworks. The uncomfortable truth is that we still understand only a fraction of what's happening in the universe around us. Every resolved mystery reveals new questions. Every explained anomaly points toward deeper puzzles. And occasionally, something appears in our data that doesn't fit any category we've previously encountered. What happens when the noise in the cosmic background finally resolves into something that we can't explain away? What if the next anomaly we discover isn't just unusual, but unmistakably artificial? Part 15. The Silent Universe. As we reach the end of our journey through the cosmic catalogue of dread, a paradox emerges that's more unsettling than any individual threat we've examined. The universe reveals itself to be simultaneously dangerous beyond imagination and mysteriously, profoundly quiet. This silence, not the absence of sound, but the absence of obvious intelligence, might represent the most terrifying discovery of all. We've travelled from the ice mountains of the Oort cloud to the event horizons of black holes, from the gamma-ray screams of dying stars to the theoretical possibility of cosmic waves that rewrite reality itself. Each threat operates on scales that dwarf human experience, wielding energies that could erase our civilization in milliseconds. Yet for all their cosmic violence, these phenomena follow predictable physical laws. We can model them, track them, and, in some cases, prepare for them. But the silence surrounding us suggests something far more ominous than mere physical danger. It hints at a universe where intelligence itself might be the rarest and most fragile phenomenon of all, or where intelligence has learned lessons we haven't yet grasped about the price of visibility in a hostile cosmos. The trajectory of human planetary defense capabilities offers a glimpse of hope amid the catalogue of cosmic terrors. From the dinosaur-killing Chicxulub impact 66 million years ago to NASA's successful DART mission in 2022, we've progressed from helpless victims to active participants in our own cosmic security. The ATLAS and ZTF surveys scan the skies nightly, cataloguing potentially hazardous objects with increasing precision. The upcoming Vera Rubin Observatory will revolutionize our ability to detect long-period comets and other threats years or decades before they pose danger to Earth. Yet even our growing competence in planetary defense reveals uncomfortable limitations. We can nudge small asteroids off collision courses, but we remain essentially helpless against the cosmic giants we've imagined. The hypothetical Thanatos and Leviathan comets, the rogue black holes drifting through interstellar space, the gamma-ray bursts that could sterilize our biosphere without warning. Against such forces, early detection becomes less about prevention and more about acceptance, the difference between dying with knowledge and dying in ignorance. The professional fears of astronomers reflect this fundamental asymmetry between cosmic threats and human capabilities. What keeps planetary defense experts awake at night isn't necessarily the known threats. We can calculate probabilities and prepare responses for asteroid impacts, solar storms, and other quantifiable dangers. It's the unknown unknowns that generate existential dread, the objects approaching from our blind spots, the phenomena we haven't yet learned to detect, the threats that operate according to physics we don't yet understand. This uncertainty extends beyond physical dangers to encompass the deepest questions about our place in the universe. Are we alone in a cosmos that generates intelligence rarely and sustains it briefly? Are we early arrivals in a universe that will eventually teem with consciousness? Or are we surrounded by civilizations that have learned the cosmic discipline of perfect silence? Each possibility carries profound implications for how we should conduct ourselves as a species. If we're alone, then human consciousness represents something genuinely precious, a brief flowering of awareness in an otherwise unconscious universe that deserves protection at almost any cost. If we're early, then we bear the responsibility of being the first intelligence to grapple with cosmic-scale engineering and the challenges of interstellar expansion. But if we're surrounded by hidden civilizations practicing dark forest discipline, then our current behavior might be catastrophically naive. Our radio emissions, space probes, and attempts at interstellar communication could be painting a target on Earth for civilizations that have learned to fear any species foolish enough to announce its presence to the galaxy. The silence itself becomes a phenomenon worthy of study. Why don't we see obvious signs of galactic engineering? Why haven't we detected the waste heat signatures of Dyson spheres or other megastructures? Why do even the most sensitive radio telescopes fail to detect the chatter of interstellar commerce or the leakage from alien entertainment systems? Perhaps the answer lies not in the absence of intelligence, but in its abundance. A galaxy full of civilizations that have learned to remain invisible would look exactly like the universe we observe, apparently empty, but actually teeming with hidden activity. The most successful civilizations might be the ones we'll never detect until we prove ourselves worthy of contact through our own mastery of cosmic stealth. This interpretation transforms every aspect of human space exploration, from scientific endeavor to existential test. Are our deep space probes being monitored by unseen watchers? Do our radio emissions mark us as a primitive species not yet ready for galactic citizenship? Is human civilization undergoing some form of cosmic evaluation whose criteria and consequences remain hidden from us? The psychological weight of such possibilities can be overwhelming. It's one thing to fear asteroid impacts or gamma-ray bursts. At least these threats operate according to physics we can study and mathematics we can calculate. It's quite another to suspect that every choice we make as a species might be observed and judged by intelligence far more advanced than our own. Yet this uncertainty also provides a strange form of liberation. If the universe is indeed silent because its inhabitants have learned to be quiet, then the very existence of that silence proves intelligence can survive and thrive on cosmic timescales. The absence of obvious galactic civilizations becomes evidence not of civilizational failure, but of civilizational success, intelligence that has matured beyond the need for conspicuous displays of technological prowess. In this framework, humanity's current situation resembles adolescence on a cosmic scale. We're old, enough to build dangerous technologies, and young enough to use them carelessly. We're sophisticated enough to detect some cosmic threats, but naive enough to broadcast our location to unknown listeners. We're intelligent enough to ask profound questions about our place in the universe, but not yet wise enough to fully comprehend the implications of the answers. The path forward requires a delicate balance between caution and curiosity, between cosmic paranoia and cosmic wonder. We must continue scanning the skies for threats while remaining open to the possibility that some of those threats might be avoiding detection as carefully as we should probably be avoiding broadcast. We need to develop better tools for distinguishing natural phenomena from artificial intelligence, while preparing for the possibility that such intelligence might be deliberately mimicking natural processes. Perhaps most importantly, we must cultivate what might be called cosmic humility, recognition that we're newcomers to a universe that has been operating according to its own logic for nearly 14 billion years. The rules of cosmic civilization, if they exist at all, were written long before Earth existed. Our survival might depend not on rewriting those rules, but on learning to follow them. The catalogue of cosmic threats we've explored, from comet impacts to black hole encounters, from gamma-ray bursts to theoretical cosmic waves, represents more than just a survey of existential dangers. It's a meditation on humanity's precarious position in a universe that operates on scales and timescales that dwarf our everyday experience. We're biological creatures adapted for life on a single planet, trying to comprehend phenomena that span galaxies and eons. Yet we persist in this cosmic detective work because the alternative, remaining ignorant of our celestial environment, seems even more dangerous than knowledge itself. Every threat we identify and characterize becomes one less unknown in the pat. The vast catalogue of cosmic possibilities. Every survey we complete, every model we refine, every defensive capability we develop, marginally improves our species' odds of long-term survival. The silence of the universe surrounding us might represent cosmic loneliness or cosmic discipline. It might indicate that intelligence is rare beyond imagination or common beyond detection. It might mean we're the first to ask these questions, or the last to answer them without catastrophic consequences. What terrifies scientists isn't just what we know about cosmic threats. It's the growing suspicion that what we don't know might be even more dangerous than what we do. In a universe that can hide entire civilizations behind veils of perfect stealth, that can harbour rogue black holes in the spaces between stars, that can unleash gamma-ray bursts without warning across galactic distances, our greatest fear might not be the monsters we can see approaching, but the ones that have learned to approach unseen. The question that will define our species' future isn't whether we're alone in the universe, it's whether we're wise enough to survive the answer, whatever it might be.